Beauty. Okay, our goal today, the big three. We want to look at inverse tan. We want to look at inverse sine. We want to look at inverse secant. And we want to find those three derivatives. The first one is by far the most common, but all three are used. And what we're going to do is we're going to figure out a way to be able to take derivatives. Then we'll look at every conceivable way of asking a question. And you're going to find is we're going to develop three formulas, none of them hard to use. And then from that point on, we now have three more derivative formulas that will look very unique. They don't look like anything else. Oh, never mind. Here's, make sure I got an eraser. So the way we're going to do these is the same way we did the logarithm. We're not going to use limits. We're going to use implicit differentiation by using the fact that we have inverses that are functions. So if y equals the inverse tangent of x, doesn't that mean x equals the tangent of y? And I can say that absolutely because it's an inverse function. Remember, we restricted the domain so that it's one-to-one, all that kind of good stuff. So what I want to do here, I want to differentiate both sides. And by the way, most of you are doing really, really good things with your notation. We're getting tighter and tighter. But some folks are putting the d dx on the other side. That'd be kind of like saying, I want the square root of 16, so let's write this. Well, no, that's the operator. It kind of has to go in front. Right? We don't multiply 16 by an empty square root symbol. We take the square root of 16. This is the operator. It says differentiate what follows it. It can't be after the fact because nothing follows it. That would be the equivalent of saying I'm differentiating nothing. So we want to do this. Well, I'll do the left side. Okay. Okay, that's my role. You guys want to help me with the right side?
Secant squared.
Secant squared of
Y.
Is that it?
dy dx.
Times dy dx. Ah, beauty. My goal was to find dy dx. What is the reciprocal of the secant function?
Cosine?
So this will be equals cos squared. You never write 1 over a trig function. Never. That's not a thing. Because not only you're going in the wrong direction, now you got to take a whole nother step just to fix it. No, you're multiplying both sides by the reciprocal. Just go straight to this. Now, I just figure out the derivative of the inverse tangent is the cosine squared of y. Are you happy with that answer? It's correct. Are you happy with it? Why not? I kind of like a function of x. You agree that that's right, but it's not useful in any way. So how am I going to fix this? Well, let's go back to the original statement. And I have a great idea. Let's draw a picture. Shall we? Can you draw me a picture where the tangent of y equals x? So in other words, what's my angle in this case? In my picture, what's my angle? The y value is the angle. In other words, there's the y. The tangent of y equals x. Well, what's tangent? Think SOHCAHTOA. So I need this ratio to be x. Can you make that real easy on me? How about x and 1? Would that work? Is the tangent of y equal to x in this picture? Yes or no?
Yes.
Yeah, be convinced. Yeah, because you know that. It's a simple trig relationship. So I need this. Pythagorean theorem, what's going to go there? 1 squared plus x squared? You with me? Okay, so let's go back to here. Can you tell me, well, let's see, cosine, won't cosine be this over this? So shouldn't this be 1 over the root? Oh, but I'm squaring it. Huh. What does that leave us with? The derivative of the inverse tan function is that simple quotient. Do you notice something lacking from our answer? Anything
Trig.
triggish? Yeah. That's the way it works. The derivative of the inverse tangent is exactly this. We just did it. I didn't tell you, we did it, and we used implicit differentiation because we went backwards. Most people think the role of implicit differentiation is weird abstract problems that aren't functions, you know, finding slopes of weird things. No, it's actually to derive half of our derivative formulas because we have inverses. Yeah.
I'm sorry, how did it turn to cosine?
How did it turn into cosine?
Not it, but
You mean how did-
had the function.
So what's the reciprocal of the secant?
Oh, the
We have
reciprocal.
got rid of it.
Okay, yeah.
Right? So we got rid of it because we have to isolate the dy dx. So let's write it right here. So the derivative of the inverse tangent of x is simply 1 over 1 plus x squared. That is awesome. And you're only going to be dealing with inverse tangents of x, never inverse tangents of anything more complicated. Or is it reasonable that you'll almost always have something more complicated than an x? Yes. In fact, between now and the day you die, if you do calculus constantly, rarely will your argument just be an x. It will be sometimes, but it's usually going to be more. I might have inverse tangent of e to the x, you know, inverse tangent of x cubed. So then the next thing we always go to is inverse tangent of u, where it's implied that u is actually a function of x. So the derivative should look exactly the same. And then the chain rule factor. So that is the most common version of the answer. So let's do some examples. Let's start with an easy one. Let's take the derivative of the inverse tan of, how about e to the x? Okay? So, start with what? 1 over 1 plus e to the x squared. And what am I going to multiply that by?
E to the x.
Which is the derivative of e to the x, just e to the x. I mean, obviously I can write this as one quotient. So e to the x over. Now, strangely enough, it is totally okay to write x squared plus 1. That's not incorrect. But you'll find that pretty much every calculus book will write it as 1 plus x squared, because that was sort of the order you found things. And plus later on when we're working backwards, it's sort of the form. It is not incorrect to switch these two. It's just, this is typically the way you're going to see it written. So it might be easier just to get comfortable. Now, what's going down here? I'd like to write it without parentheses.
2x.
Okay, I'll do my part.
X squared. 2x.
Oh, good, we have an argument going. What's the rule when you raise something to a higher power? What do you do with the exponents?
Add them.
Multiply. So what's the exponent?
2x.
2x. E to the x when I square it becomes e to the 2x, not e to the x squared. I'm multiplying those guys. So if this had been x to, you know, e to the x to the 10th power, then this would have been a 10x. Can I cancel anything? Can I break apart that quotient? You really want to cancel those e's, don't you? Can you? No, because it's not a factor in the denominator. I can always break apart a numerator. I can't break apart a denominator. Okay? And we know that, but sometimes we get confused. I know that I can do this. A plus B over C, that's AC, BC. I can do that, and sometimes it makes it easier because I can simplify. But the mistake we sometimes make, because it looks similar, and you know, we do it occasionally. I have A over B plus C. Is that A over B plus A over C? No, can't do that. Can't break apart a denominator. That would never be true. So, that yes, that no. Okay, so this one here, that's as good as it gets, but there was nothing about that was complicated in any way. Okay? Let's try another one. Let's do, how about let's do the inverse tan of x plus the log of 1 plus x squared. I would like dy dx. Now, this is not an exam question because we don't have this on our first exam, but certainly could come up later on in the course, right? Because we've already done logs earlier. Now, the reason I'm putting these two together, they're strange, very strange bedfellows. Natural log and inverse tan. You can't get much more different, right? One's an exponential function, one's an inverse trig function. But strangely enough, their derivatives, depending on the functions, sometimes their derivatives look really, really similar. So what's the derivative of the first one? Beautiful. How about the second one?
2x over 1 plus x squared.
Would you say there's a similar vibe there? They have the same denominator. Oh my gosh. Can I make that into one quotient?
Yeah.
Again, don't worry about what order you write things. Can I factor anything out of there, simplify anything, or is that it? What do you think?
Taxes.
Are we done, or can we keep going? If you're not sure, then what's the answer? You're done. Yeah, absolutely every time. If you're not sure, you're done. Don't take a chance on making an error. No, actually, you can't go any further with that one because neither numerator nor denominator factors. But point is, these are two very different functions, but my derivatives actually look very similar. Okay? They're never going to be the same, but they can look similar because of the way we did the derivatives. So inverse tan, very happy function. Now, I want to go to the answer and see if we can make some sense of it. Okay? So, if I'm thinking of, let's start with the tangent function. We know the tangent function looks like this. By the way, this is not horizontal here. The slope of the tangent line at the origin is actually 1. We know that. Now, what does the inverse tan look like? Well, that's actually simple. If I know what any function looks like, its inverse, I just remember, flip it over the line y equal x. So this would be y equals tan x. Remember, this would be x equals negative pi over 2, x equals positive pi over 2. So this will be y equals negative pi over 2, y equals positive pi over 2. And then this graph will look like, okay, this is the graph of now let's look at the derivative, shall we? The derivative, which I have over there also. Now, at the origin, if the slope of the tangent line here is 1, what do you think the slope of the tangent line here is? It would also be 1, wouldn't it? Because I just flipped it over. If the slope here was 2, the slope here would be 1/2. Because x and y changed places. So change of y over change of x would become change of x over change of y. That's a fairly simple notion. The derivatives would be reciprocals in that case. So that slope is 1. What's happening to these slopes as x gets closer and closer and closer to pi over 2? They're getting bigger and bigger and bigger, aren't they? So the slopes here are growing without bound. What's happening to the slopes here as x grows without bound and y gets closer to pi over 2? Aren't the slopes flattening out? Does that make sense? These are growing without bound. These are approaching 0. So now let's look at this. When x is 0, I am 1. And we just said the slope of the tangent line at the origin ought to be 1. And as x gets bigger and bigger and bigger and bigger, what's happening to this value? It's getting closer to 0. By the way, does it matter whether x is positive or negative? No, the slope is still getting closer to 0. So does that derivative actually agree with this graph? Yeah, perfectly. It perfectly agrees. As x grows either positively or negatively, my slopes approach 0 positively. Because those slopes are always positive, aren't they? So that makes sense. So I always like it when we can make the derivative make sense. When we first did the derivative of the sine function and we got the cosine graph, remember we drew it? That you go, okay, that makes perfect sense. Same thing here. I don't need you to remember every aspect of trig, but if you remember what the tangent looks like, then this is a piece of cake. Then equating this to this in terms of the slopes of the tangent lines, fairly simple thing. Okay, let's go on to the next one then, which will be the inverse sine function. We're going to do it the same way. We're going to start by rewriting it in reverse. I don't seem to have any black pens up here. Okay, I guess we'll stick with over here. Thank you. So if I start with x equals the sine of y, if y equals the inverse sine of x, then x has to equal the sine of y. Remember, we restricted the domain, so it's only a small piece. Now let's differentiate both sides with respect to x. Okay. Take a second. I want everyone to do this on their own for a moment and see if we all come up with the same thing. Here, I'll do my part. What goes on the left?
Cosine?
Cosine.
The left.
Oh, one.
Oh.
How about one? What goes on the right?
Cosine of y times dy.
Cosine of y
dy dx.
times dy dx. Beautiful. Okay, therefore, dy dx equals
Cosine of y.
Secant.
so reciprocal
Secant.
secant y. Okay. Waiting for somebody to blurt it out. People say, well, don't you divide? I never divide. Never. Ever. I always multiply by the reciprocal. Why? Because dividing is never faster, it can only be longer. At best, it's a break even. No, always multiply by the reciprocal, and that's always the right answer, but you might not have to simplify that thing. If you divide, you almost always have to simplify it. And if you don't simplify, then it makes the problem a lot more challenging. Okay, let's do what we did before. I need a picture, go back to this picture here. The sine of y equals x. X is the ratio, y is the angle. This is so, ka, toa, so we're on so. So would be what?
Opposite of hypotenuse.
So I need the ratio of this over this to equal x. So what goes where? What's here?
X.
What's here? 1. If you got that, you got this nailed. So that was pretty complicated though, right? Okay, I think we got that one. Now, Pythagorean theorem, what's going here? 1 squared minus x squared. Beautiful. Because the hypotenuse is 1 this time. So this is not the same triangle we had for the tangent. Can't be. So now, dy dx equals the secant of y. Well, secant, you know, is the reciprocal of cosine. So if cosine is this over this, then what's secant? This over this. Oops. That's not a rational function, but it's still, you know, I got a polynomial under a square root. There's nothing triggish. Again, that one's a little bit tricky, isn't it? So I want to do the same thing we did with the tangent. I want to look at the graphs. That is the right formula. But there's got to be a feel. It's got to make sense. Not just, okay, we derived it, we got it, great, let me just run with it, but I don't really know what we just said. Okay? I was talking with one of my students, Calc 3 students, we were talking about physics and engineering and stuff. And I said, were you lucky enough to start the physics in Calc 3 or did you have to start in Calc 2? He says, no, I started in Calc 2. The disadvantage is you're learning all of your vector stuff from your physics teacher. It's not their role to teach you the vector stuff, but you need it to answer the questions. At Mesa College, you can take chemistry without having had intermediate algebra. What's the big deal? You use logarithms all through chemistry. Do you want to learn your logarithms in chemistry, or do you want to learn them in a math class? math class. But the chemistry teacher's got to teach you just enough to get by, which means you can answer questions, but you don't necessarily have any idea what you said. In physics, you can answer questions, but you don't know what you said. But if you waited one semester to start your physics sequence, you've learned all the vector stuff in calculus, most people tell me, oh my gosh, now it's so easy. All of you can tell me that this is a formula and answer questions directly, but could you explain what the heck's going on? Because if you can't, then what good is the answer? In fact, how do I even know if the answer makes sense to me? But let's look at a simple graph. Now remember, we restricted the domain of the sine function. Remember what we did? We went from here to here, from here to here, because now it turns around. So this is pi over 2, this is negative pi over 2. Right, with the tangent function, we just did one period, and then right, it goes forever and ever and ever in both directions. So if that's the sine, then the inverse sine, we know that the slope of the tangent line right here is 1, because we know the sine function looks just like the line y equal x, really close to the origin. So the inverse sine is also going to have a slope of 1, but where this goes horizontal, this is going to go vertical. So a reminder, this is 1, this is negative 1. So that means this is negative 1, this is 1, this is pi over 2, this is negative pi over 2. And this tangent line and this tangent line would be vertical. But do you agree that all of the slopes are positive here? That's important. They don't change signs. So what did we just say that the derivative was? Because we like the formula to kind of go with the picture. Okay. All right, so when x is 0, don't I just get a 1 here? Which means the slope of the tangent line right here is 1. And as x gets bigger and bigger and bigger, well, how big can x get? X can only approach 1 from the left. Oh, but as x is approaching 1, what's happening to 1 minus x squared? What's that approaching? 0 from the right, which means your quotient is approaching huge, right? Your quotient is growing without bound. These lines, what are they doing? They actually become vertical at the very end, which means your slopes are growing without bound. Now what about on the other side? What if I'm approaching negative 1 from the right? This is still approaching 0 from the right. So my slopes are still growing without bound positively. So again, does this derivative match this graph? Hopefully it does. Right? At the origin, that's easy. And as I go this way, these are growing without bound positively. These are growing without bound positively. Right? My denominator is approaching 0 from the right, so this is growing without bound positively. So the derivative does match the behavior of the graph. Okay? That's important. Now, in trig, you may have spent time graphing inverse functions. Know what a sine wave looks like. Then you know how to manipulate, you know, the cosine. Be aware what an inverse looks like, because sometimes we have to manipulate it, but not that often. This is pretty much the only time you're going to need to know what it looks like. So, if y equals the sine of x, we now have dy dx equals 1 over 1 plus x squared under the root. So then the first thing, obviously, is to say, where does the chain rule fit in? So y equals the, inverse sine of x. Y equals the inverse sine of u, function of x, then dy dx has the same form, and then of course multiplied by the chain rule factor. Okay? All of our derivatives have that form in the end. So let's do an example of this. So y equals the inverse sine of, how about, I don't know, x squared plus, let's just say x squared plus 2x, something icky like that. Then what is dy dx? I'll do my part. What's going down here?
1 minus x plus 2x. X squared.
Parentheses.
Ah,
And then you square.
anything else?
Times the derivative.
And what would the derivative be?
2x plus 2 looks like.
Could I do that?
Mm-hmm.
What do you think? Can we do that, everyone? Yeah. Can I factor the numerator? Well, I can factor a 2 out, but that's not a factorization. Factoring out a coefficient, because the coefficient can't be 0. So I can factor the 2 out, I can leave it alone. Here's the question. Is the denominator simplified? I have 1 minus a quantity squared. Is that simplified? Is it simplified? No, because I'd have to square the quantity. Here's the question. If I square that quantity and then distribute the negative, I'm going to have negative x to the 4th, negative 4x cubed, negative 4x squared plus 1. That's going to be my new term under the root. It's correct. Is it an improvement? That, by the way, the answer is not obvious. I'm going to give you a hint though. In a few more weeks, when you guys know what's coming up, the dark side. When we cross over to the dark side, I'm going to ask the question and say, where did it come from? And if I ask the question in this form, good luck figuring out where it came from. But if I ask the question in this form, it's actually fairly simple to go backward. So which version do you think is more useful? The first version or the second version?
First.
Probably the first one. So it's not simplified, that's true. But if I have to manipulate this and use this, heck, if I got to do this on my calculator, which one's going to require more button pushing? I think that one will. So I'm totally okay. Now, the difference is nothing combines. What if I had terms that would actually combine or cancel? Well, then maybe I do want to distribute. But that's more of a choice. So remember, I've asked the question before, and I'll ask it again. What is the most useful form of the answer? Not what's the most correct. Am I going to use this in a future calculation? Well, the answer is always yes. In this class, that's the end of the problem, isn't it? There's nothing else to do. But in the next class or the physics class, no, this is the beginning of the problem. There's a whole bunch more to do. So what version is going to be easier for you to manipulate and work with? Am I going to, at some point, take the sign of my answer or the cosine? Am I going to do something else? Well, if I'm going to have to enter buttons on the calculator, right now I'm going to have to equate this at various values. I probably want, the way I like to say it, I want the least x's. That's why I'm more of a fan of this than I am this, because this is just less button pushing on my calculator to get the same answer. Okay. It's not about right or wrong again, it's about what's the most useful form, as long as it's correct. So the inverse sine, not too bad. Now let's do another one. How about we have, let's see, maybe a product rule problem. I want to do, we want to find dy dx. Because this is the kind of stuff we'll end up doing. Now, I asked inverse sine of x, not inverse sine of a function. So that makes it a little easier, but I've also got a product rule going on here, and there's probably a chain rule inside of there too. So, do you want to just start by writing derivatives, or do you want to do something first? Does anybody want to change the problem before we take a derivative? What do you want to change?
The root.
What do you want to change it to?
3 halves.
1 minus 2x.
What power?
3
For like 3 different.
3 halves.
The root is the denominator, so it's 3 over 2. I heard 2/3 and I heard 1/2, but I didn't hear what? 3 halves. It does matter. Now, if I do this, I don't know what the final answer is going to be, but I suspect I might be able to get some simplification later. Not worried about it yet. All right, so straight up product rule. So let's say it out loud. First, times the derivative of the second. But rather than write d dx of the second and then take the derivative in the following step, let's just go ahead and take the derivative now. We can. So times what?
1 over the root of 1 minus x squared.
We good with that? Plus the second times the derivative of the first.
3 halves 1 minus x squared to the half power times 2x, negative 2x.
Beautiful. Okay, stop. We're done with the calculus. But as you've probably discovered so far in the last couple weeks, there's usually a lot more to go, right? Everything we said is true and correct, but this is probably not a very useful form of a final answer. Now, I want to factor, I want to do GCF, I want to factor, well, actually, before we do that, can we do something with that?
Isn't it just,
Could I write this as 1 minus x squared to the negative 1/2? Would that be legal? Why would I want to do such a thing? Because they're the
because then you
same
could
thing.
just have it, yeah,
Now what do I want to do with the exponents?
subtract, well,
I want to add them. Ah, this is when I add the exponents. That would be a way better answer and a lot more useful, certainly. Okay, so if I add those, bring this. So what does that become? My first term is now just 1 minus x squared to the first power, isn't it? Times, or nothing, that's it. That's the whole first term, okay? Plus, or maybe minus.
minus 2x times,
Well,
inverse.
can I go like that?
Oh, yes. 3,
So minus what?
3x.
Now it's a question, what order do you want to write things? Does it actually matter? The only thing that matters is the 3 goes in front, but I think most of us would agree we'd probably want the 3x in front. Does it really make a difference which one of these goes where, you think? Probably not. So I'll just keep it in the same order. We'll see if it matters in a moment. And then what was the last one?
1 minus x squared to the power of 1/2.
What, now, whether you write it as a root of the power 1/2 actually doesn't make any difference. Oh, I wrote it as a root. Is this correct so far?
So far.
Is this the bestest, most usefulest final answer I can possibly give? Let's go with what you said. You said 1/2 power. That will make that question very obvious. Is this the bestest, most finalist answer I can possibly give? No, because I have a common factor. Oh, and we always factor a derivative if we can. So what's the common factor? 1 minus x squared or to the 1/2 power?
The half.
The half power. So if I pull out the half power, and again, I don't care if you write this as a root or half power, it's the same thing. What does that leave me with?
Root
1
1
minus
minus
x
x squared.
Whoops. 1 minus x squared
And
to
then
what power?
minus,
To the half.
To the half power. That guy's gone.
Minus 3.
and then sign it first.
Now, if you choose to write this as a square root, then write this one as a square root. Do them both or do neither. It makes no difference. Now I have it in a factored form, and there's really nothing else I can do. Okay? Can't squish these together, there's nothing common, so I just walk away. This is a better answer because it's factored. We might not have seen that there was a factorization, but it's factored. And going back to the beginning, if I didn't recognize this could be simplified, I may be representing my final answer far more complicated than it needs to be. Okay? Question. Can I just write this as 1 over sine x? It's an absolute mathematical statement.
That's not a power.
That is false, always. Of the infinitely many things you could possibly come up with, it's never true that an inverse equals the reciprocal of the function. This is not an exponent, this means inverse. Inverse does not mean reciprocal, period. There's no function where inverse would mean reciprocal. okay? The only operation where inverse equals reciprocal is multiplication. But that's not a function, that's an operation, that's not the same thing. So in the end, probably that. You know, if you got this far, I'm happy. I'm thrilled if you get that far, because that means you manipulated the answer. But again, it's the algebra that gives us more trouble probably than calculus on these, right? Because there's so many steps. So inverse sine is a little ickier than inverse tan because there's a square root involved, okay? Not that big a deal. Now the last one is a little bit on the tricky side, just a little bit, and I'm going to show you why. Okay, so now we want to consider the inverse secant. This is the only one that has its own special rule. Of all the derivative formulas there is, this one has its own special rule, and it doesn't come up a lot, but it does come up occasionally. Right? I want to do the derivative, so like before, we start by writing x equals the secant of y. Okay? Then I would differentiate both sides like before. And walk me through.
1, 1, 1. Again, times tangent.
So secant y, tan y, dy dx. I don't care if you know this by heart. At the very least, you should have the formulas, you know, just right there next to you at all times. So throughout the semester, after repetition, right, you know it. At the end of this semester, you will be expected to know all your formulas. Well, when? Well, 5 minutes after the final exam. Because then every class you take after this, you'll be expected to know the formulas. So you have all semester to learn them and practice them, but have them written down in a convenient place so that you're not waiting for somebody else to answer the question. Okay? What happens is you will get rusty on some of them. There are some that are far more common than others, and those ones we don't question. You'll know them inside and out. The more obscure ones, you probably want to have written down next to you so that you don't have to, you know, wonder what the answer is. So, this one's a little tricky. What does dy dx now equal? Well, what's the reciprocal of secant? Cosine. And what's the reciprocal of tangent? Cotan. This is the answer, but it's not useful because I need these to be functions of x. So we'll go back to our triangle like before. And again, I'm going back to this statement here. The secant of y equals x. Well, let's see. Ka is this over this, so secant is this over this. I need that ratio to be x, so x and 1. Will that work?
Wait, sorry, can you repeat that? Just repeat what you said, sorry. My brain buffered.
Ka, cosine, so secant, go the other way. Right?
Okay.
If this is cosine, then this is secant. So what goes here? Pythagorean theorem. X squared minus 1. Good. So, what does this give us? Well, the cosine, right? So what is that?
1 over x.
And the cotangent, now cotangent. Tangent is this over this, so cotangent is this over this. That's the easiest way to remember it. I have the product of two quotients. Could I just write that as 1?
Mm-hmm.
Yeah, that would be way more efficient. That would be way more efficient. Now, this does bring a slight problem. Slight problem. And here's where it gets a little bit weird. So I'm going to show you. I don't want you to memorize a result because it won't mean anything to you. So I'm going to show you. If you remember how we came up with the graph the other day, we looked at a cosine graph and just flipped it. So we're going to do the easy route. So what I'll do is I'll make the cosine really bright. So So now I want the reciprocal of this, which means that I would automatically have asymptotes here, here, here. Yeah, this is the easiest way to possibly conceptualize this. Now, what we did the other day was we said, let's use the same restricted domain that the cosine had, which was 0 to pi. And if I do 0 to pi, this is pi, by the way, I'll sweep out every positive and every negative value, correct? You all with me on that? Now, as I move left to right, tell me something about the slopes of these tangent lines. They're always positive, they're always positive. Now, I'm not even going to bother drawing the graph of inverse secant, but remember I said the slopes of the, when you're doing an inverse, right, change of y over change of x becomes change of x over change of y because you swap the roles of x and y. So if my original function only has positive slopes, then its inverse will only have positive slopes. Go back to the other definition. Remember, something is only one-to-one if it's always uphill or always downhill. But if something's always uphill, its inverse is always uphill. If something's always downhill, its inverse is always downhill. They go hand in hand. So for the inverse secant, whatever it looks like, with this thing flipped sideways, that's all it is. All my slopes would be positive. But I can ask the inverse secant of anything, really. Because don't I have negative y values? But if all my slopes have to be positive, look at my formula. Is that quotient always positive? For all real numbers x, is that quotient always positive? By the way, I can take the inverse secant of any real number that's not between -1 and 1. Because the secant returns all real numbers except values between -1 and 1. So I can do the inverse secant of a positive real number, of a negative real number, huge, just not between -1 and 1. I can do the inverse secant of a negative number, that's not a problem. The problem is, the derivative of inverse secant is going to be negative exactly how often? Half the time. Oh, we just said that the slopes are always positive. But if I insert a negative value for x, I'm going to get an impossible answer. How do we fix that?
Absolute value.
There's an absolute value in almost every calculus book. There are some calculus books who define it completely different, and it's a problem because you actually will get different numerical answers. I'll give you a hint, your calculator is programmed for this one. People who program calculators use the main version. But I said this was an area that mathematicians are not in absolute agreement on. Most of the people go with this route. That means when I do the derivative of inverse secant, I technically am going to have an absolute value here that I have to consider. Now, if that quantity is always positive, then there's no worries. But for now, we'll leave the absolute value in there. And I know it's kind of a crazy thought. So let's write it down. At first glance, a lot of people confuse this one with the inverse sign because of the square root. But you notice the order of subtraction's not the same because x is the bigger number in this case here. Now, let's go to the chain rule version. So what if y equals the inverse secant of u? Well, then dy dx will equal 1 over the absolute value of u, square root of u squared minus 1, and then times du dx. So inverse secant is kind of unique in one really specific way. When you're doing the derivative of inverse tan, I would be hard-pressed to make up a problem where you could actually reduce your answer. It's just not going to happen. Right? You're going to have a quotient of things that have no common factors. The inverse sine's derivative, you're never going to have any cancellation. But strangely enough, when you're doing inverse secant, it will often be the case that you can reduce your quotient. I'm going to do a couple of examples. Okay? Let's start with an easy one. Let's say I'm doing the inverse secant of e to the x. Okay? Then dy dx is. And by the way, as we said before, if this here is not a quotient, it's usually easier just to stick it up on top, isn't it? If it's not a quotient. If it's a quotient, no, write it as a product. That will be easier. So let's do this. So what do I got? 1 over the absolute value of e to the x. By the way, what's the absolute value of e to the x? Isn't that just e to the x? Because e to the x is always positive. So we will be able to undo the absolute value here. Square root of e to the x squared, I'll write it out, minus 1. And then I'm multiplying that by, my eraser.
Right there on by your
Oh.
briefcase.
He's managed to hide it really well. And now what am I multiplying by? What's my chain rule factor?
EDX.
Do we agree that the absolute value of e to the x is e to the x? Then can I do that? Is that legal? Yeah. Is that encouraged? Yes. So give me a bestest, most finalist answer.
E to the x. E to the 2x
E to the 2x
minus 1.
minus 1. The e to the x is canceled. Only the inverse secant has this property that it's possible. It's not always the case, but it's possible that you're going to get cancellation. That your chain rule factor and your original u often will cancel. Let's do another one like this. Keep it simple, x to the 4th power. Now, that x can be positive or negative, that's not an issue. So what do I write? What's going under the root? So well, I'll write it as x to the 4th squared, which is x to the 8th, minus 1, and then the derivative of x to the 4th, which is, I'll put right here, 4x cubed. Now, that's already strictly positive. So in the strictest sense, I really need an absolute value around that guy more than that guy. Can I cancel x's? Do the x's cancel? Yes. But this one looks a little bit tricky algebraically. I'm going to show you. That's definitely x to the 8th minus 1. I have one more x on the bottom than I do on the top. Are you happy with this as a final answer?
No.
Why?
Absolute value.
Because that x can still be negative exactly half the time. Absolutely correct. No pun intended. Okay? Did everybody catch what we just did? Because x can be negative half the time, if I don't put the absolute value, that means I'm giving a negative result half the time. Oh, now it feels redundant putting it here. But putting it here only reminds me to make sure it showed up in the answer. If my argument is x to a power, then I know the derivative is going to be x to a power of exactly 1 less, which means everything but 1x will cancel. So if I put x to the anything here, I'm going to have an absolute value of x in the denominator. So the form of the final answer is really nice and clean. Here's the tricky part, working backwards. Working backwards from this one is actually tricky, but we're many weeks away from that one. Okay, questions so far? All right, so we've just looked at 3 different inverse trig functions. There should be a question asked here. We've looked at inverse tan, inverse sine, inverse secant. We've looked at all 3 of the possible inverse trig functions, right? All 3 of them. Wait a minute, aren't there
3 more?
3 more? Are we just ignoring them? Well, not exactly. Let me do one of them. I'll do the inverse cosine because it's the easiest of the remaining ones. All right, let's consider this. Now, inverse cosine and inverse sine are not the same thing, but we restricted the domain of the sine function to be negative pi over 2 to pi over 2. We've restricted the domain of the cosine function to be 0 to pi. All of our outputs are now numbers between negative 1 and 1, so I can do the inverse cosine or the inverse sine of any real number between negative 1 and 1, and I'm going to spit back an angle. Okay, we know that part. So if I do x equals the cosine of y, and let's continue just like we have and see what we get here. And then you'll understand why we don't need all of them. All right, so the left side is, the right side is
Negative sign.
negative sine y dy dx. So dy dx is negative, what's the reciprocal of the sine function?
Cosecant.
Cosecant. We don't like cosecant, we really don't. Cosecants and cotangents from a calculus point of view are really not very friendly. But they're there, so occasionally we have to work with them. All right, so let's continue. I need a picture where the cosine of y equals x. Cosine. This over this has to equal x. So x, 1. And what goes here? 1 minus x squared. Sine is this over this, so cosecant is this over this. Okay, are you guys experiencing an overly abundant sense of deja vu? Haven't we seen this derivative before? Well, not exactly, but we saw a derivative that looked a lot like this. I mean, what was the derivative of inverse sine? Wasn't it that? So isn't this just the negative of the derivative of inverse sine? This is why you never work with inverse cosine, because its derivative is just the negative of inverse sine. So I'm going to give you the other three right now. I'm not going to derive the other two. This is a really, really handy identity. The derivatives of the three inverse co-functions are just the negatives of the original three inverse functions. Wait a minute, that's the language I just used. Something about derivatives of co-functions being negatives of derivatives of original. Does that sound familiar to you guys? Mm-hmm. Isn't that something I showed you, that the derivative of cosine, cosecant, cotangent were just the negative of the Yeah, there's a relationship there. Now I want you to look at it this way. Inverse cosine of a ratio returns an angle. Okay? I'm taking the derivative of that rate of change. We are not saying that the inverse cosine is equal to the negative of the inverse sine. That is not true. But we do know the inverse cosine and the inverse cosine and the inverse sine only differ by a constant. Think of when you guys know there's some simple identities with sines and cosines. You know, if you add or subtract pi over 2, things like that. If I think about it in terms of a graph, I'm going to give you a really simple one. Okay. I know that the sine function looks like this. The cosine function looks just like that, except it's shifted. Yeah. It's shifted exactly pi over 2. Okay? So I take my cosine and then I add, right? I'll get the sine if I just simply add to the angle. So what would it be? Cosine of x plus pi over 2 equals the sine of x? Something like that? Yeah. I'm taking the cosine of an angle and I'm returning a ratio. So if I do the inverse cosine of the ratio, I get the angle back again, which means that if I have inverse sine and inverse cosine, those answers, returning angles, are going to differ by pi over 2. Oh, and so if I have two functions that differ by pi over 2 and I take both of their derivatives, isn't the derivative of pi over 2 0? See, that's why we work backwards. I can also do this as a minus, by the way. So again, kind of an easy way to think about it. Inverse cosine is going to return an angle. Inverse sine is going to return an angle, but it's not going to be the same angle. Those angles are going to be differing by a little bit. Okay? That's why they're constant multiples of each other. So if you ever run into a situation where you're having an inverse co-function and you're doing the derivative, just remember it's the negative of the original guy. Okay? So you do not need to know the three co-functions because of that relationship. That's why we only do those three. And that also means that working backwards, you could never get an inverse co-function as an answer. Now I always look, one of the first things I look at when I'm looking at a calculus book, I'll look at the very back of the book. They have what is called a table of integrals that's in the future. And I look for how many incorrect answers they have. And a lot of times there are many incorrect answers. Why? Because they just copied off somebody else's table. They all use the same tables, most of the textbooks, and usually they're bad. And many of them are incorrect, and they didn't know how to check them. Back in the day, there was no technology to check them. But there are certain answers that are impossible to get. When you're working backwards and you're getting a logarithmic answer, you can only get a log base e. You can't get a base of it, any different base when you're working backwards. I can start with a different base. We know how to convert it to log base e and then do the calculus. When working backwards, you can only get a log base e. There are certain things that that's the way it'll work. And it's actually convenient. You don't have to worry about multiple possible answers. So, if nothing else today, you can now differentiate any inverse trig functions. So how many functions do you have right now? How many functions do you have? Well, let's think about it. We have the power rule, right? X to a power, but that's any type of power. We have 6 trig functions. We have e to the x, but now we have a to the x. We have log base e, but now we have log any base e. And now we have these 3 guys. So how many is that so far? I think I just counted with my fingers. 14 so far? We're not done. And that's not counting product rule and quotient rule and chain rule, which just sort of applies across the board. There's about 20 plus derivative formulas altogether that we're going to know. There's still quite a few more. And then when we do the reverse process, if you go in one direction, then we'll learn how to go in the other direction. But there's a lot. This is why I want you guys to have those formula sheets around. Not to memorize, no, to familiarize. In my higher level calc classes, they're supposed to know all these. So I encourage them on day 1, print that formula sheet. All of my classes get the same one you guys got. I say print it out, have it right there. So when we're doing a problem, you're going, okay, it's right here, it's right here. After a while, guess what happens? You stop looking at the sheet. Because we do them all so often that you just start recalling them. But then there will be those folks who never answer the question. They always sit, sit on their hands, don't answer the question. And then when it comes time to take an exam, and you actually are expected to know every single calculus formula because no one's ever going to let you write them down, they get stuck and they can't answer all the questions because they can't remember all the versions. You kind of have to, right? Most people here don't struggle with their quadratic formula, the point slope formula. You use them so many times that you just need to see it once and you remember it. The calculus formulas are really similar. Most of you will probably be taking differential equations at some point, not 255. Everything's just automatic at that point. You don't even think twice about it. Your calculus formulas become more like your quadratic formula. They're just automatic things because you've used them so often. But when you're first learning them, it takes a while. That's why I want you to have them written down. You're going to write them down for the test. That's not even a thing. I worry about the future semesters. Right? If you don't learn them in this class, it's really rough later because that means you'll have gaps and you'll have holes. Okay? I think we're probably at a good stopping point. So let's go ahead and do that. Let me do the roll thing. I want to